We previously saw that alkynes will undergo some of the same reactions as alkenes will. And alkynes will also undergo catalytic hydrogenation. So that means adding hydrogen to those degrees of unsaturation that are present. And so if we start with an alkyne and we use hydrogen with some type of catalyst, now recall that the catalyst is going to be something like palladium plated on carbon or platinum plated on carbon, some kind of a metal catalyst to help facilitate the hydrogen binding to the degrees of unsaturation. What we'll see is with one equivalent, we'll reduce down to an alkene, but the alkene is not easily isolated from this process because it's just too reactive. So it's hard to get just one equivalent of hydrogen exactly. Hydrogen is a gas. And so what will end up happening is the alkene will react with more hydrogen that's present and reduce all the way down to an alkane. So just as we saw in the last chapter on alkenes, if we have something like 2-butene and we react it with hydrogen with platinum over carbon, our product is going to be 100% butane. If we have an alkyne and we perform this reaction, hydrogen with our catalyst, we're also going to get the exact same product. It will 100% be converted to butane. So you're going to get alkanes if you're using a catalyst with hydrogen. For example, if we start with 4-octine and we use our hydrogen with a catalyst, we'll talk about what this no poison means in a second. You get octane as your product. You can see where 4 atoms of hydrogen were added because we had 2 degrees of unsaturation. So right across the triple bond. You might wonder if there is a way to actually reduce an alkyne to an alkene without going all the way down to the alkane. And you cannot do that with hydrogen in a catalyst, but if you use something called a poisoned catalyst, which a poisoned catalyst, you can think about it like being a more selective or bulky catalyst that allows you to stop at that intermediate alkene product. So first we're going to start on how you produce cis alkenes, or in other words, Z alkenes, where you end up with the hydrogens added to the same side or the same face of the alkene. So this would be called syn addition. So what you'll often see over the line is something referred to as Lindlar's catalyst. This is a poisoned catalyst. There are other poisoned catalysts, but this is just kind of the common one that you want to be familiar with. Lindlar's catalyst is a heterogeneous catalyst, which means that it is consisting of species and substances that are in different phases than one another, and it consists of palladium deposited on calcium carbonate, so PdCaCO3, and there's also lead acetate present, and another organic molecule known as quinoline. Now, you don't ever have to redraw or regurgitate what makes up Lindlar's catalyst, but you can see that there's a lot of things going on. We still have some of those precious metals that are used for plating purposes. Hydrogen still is one of the reactants as well. And there's other things that make it bulky and selective and slower. So when you see over the line Lindlar or Lindlar's catalyst, that is the chemist's shorthand for indicating that you're going to be forming Z alkenes or cis alkenes. So you often won't see any of this other stuff. Those are just other poisoned catalysts. Really, they should also write H2 and Lindlar's catalyst, but a lot of times I'll see sometimes they just write Lindlar's catalyst. So if we were to start with an alkyne this time, and we had hydrogen and the Lindlar catalyst, our product would be an alkene, and it would only be the cis stereochemistry that we would see here. So we would not end up reducing all the way to the alkane because we have that selective, bulky, poisoned catalyst. Now there is also a method in order to produce E-alkenes or transalkenes where the hydrogens are added to opposite faces. And this is often referred to as the dissolving metal reduction. It is not a reaction that we would learn the mechanism of just like any of the hydrogenations, but it actually involves using ammonia and sodium metal. So the ammonia has to be used at really low temperatures because its boiling point is negative 33 degrees Celsius. So this reaction has to be cooled down very low. And the alkali metal, or sodium or lithium, whatever is being used, is just a source of electrons. So this reaction proceeds through a radical anion, which that would be having an unpaired electron that's free. So we're not going to go through the mechanism, but what you want to know is that you end up getting a trans or an E-alkene as your product primarily when you perform this dissolving metal reaction. So this slide is just a review of a few of the hydrogenation reactions that we just talked about. So on the left-hand side, we have an alkyne with its 2 degrees of unsaturation. If we use an alkali metal such as sodium in liquid ammonia, that's that dissolving metal reduction, you end up with a transalkene. If we use hydrogen with a poisoned catalyst such as the Lindlar catalyst, we end up with a cisalkene, so Z versus E. Same thing over here, you can see there's that dissolving metal reduction, an E-alkene was produced. Here's the Lindlar catalyst, a Z-alkene was produced. And if you start with an alkyne and you have just hydrogen with palladium or platinum over carbon, you end up with an alkane product. So the reduction goes all the way down to an alkane. Alkynes can also undergo oxidative cleavage, as we learned when we looked at alkenes. We're not going to look at the mechanism, but recall that one of the common agents for oxidative cleavage was using ozone. So ozone was O3, and it had a Lewis structure like this, where we had a separation of charges on the oxygens. It's not the only reagent that can perform oxidative cleavage, though. So notice here we have two alkynes that we're starting with, and we can use ozone with a reducing agent after, such as dimethyl sulfide. So we would have a sulfur bonded to two methyl groups. Another one is H2S. You can see the structure is very similar to the dimethyl sulfide, the DMS. Both of those are reducing agents in that second step, just like they functioned as reducing agents with alkenes. Another set of reagents that will give us the oxidative cleavage products is potassium permanganate in acidic conditions, such as HCl. So when you see either of these reagents, know that you're going to break the sigma bonds and the pi bonds of the alkyne. So cleavage means breaking them in half. What we end up getting is products that are at a higher degree of oxidation than our alkenes were. Recall with alkenes that we formed aldehydes and ketones as our products. When we're dealing with alkynes instead of alkenes, we form carboxylic acids. These carboxylic acids are at a higher degree of oxidation than aldehydes and ketones are. Those are at a lower degree of oxidation or a lower oxidation state, just like alkynes are a higher oxidation state than alkenes. We'll go into oxidation numbers and oxidation states more in general chemistry too, but you're going to want to know just for now that alkynes are higher than alkenes, and therefore their products are at a higher oxidation state than alkenes would be. So when we break them or cleave them, we end up getting two products, depending upon what the initial reagent was, and we're going to see carboxylic acids. So you're going to want to count, and we can use the black dot kind of as a marker. So here we have 1, 2, 3 carbons there. Off of number 2, there is a methyl group. So this would correspond to this carboxylic acid. 1, 2, 3, and then here's that methyl group at position 2. So when drawing our product, position number 1, where it breaks, is where the oxidation is going to occur. So at position number 1 is where that carboxylic acid is. But notice we didn't gain or lose carbons. There's still the same number of carbons. And then on the other side, you would have 1, 2, 3 carbons. And so that corresponds to 1, 2, and 3 on this right carboxylic acid. And at position number 1 on the other side is where we have that oxidation occur. That's where we have our carbonyl and where we have our alcohol group coming off. So together that's a carboxylic acid. Just make sure that you're counting your carbons when you're drawing products of oxidative cleavage so that you're keeping the same number of carbons on the left and on the right-hand side. The next class of reactions that we're going to look at are special to alkynes, and they involve a terminal alkyne specifically. That's one where there is a hydrogen bonded to the alkyne because the alkyne is present at the end of the molecule, versus an internal alkyne where the triple bond is somewhere in the middle of the molecule and there's no hydrogen coming off of either side. Instead, there's a carbon and a carbon there. So for all of these reactions, we're going to be starting with a terminal alkyne. That terminal proton that's on the end of the alkyne is considered acidic. It can be removed by using a very strong organic base. Now there's lots of organic bases. We're going to look at 3 of them that you should be familiar with that will be strong enough to deprotonate that proton. You might recall that it's harder to remove a proton from an alkane or from an alkene because of the orbitals that are being involved. And so they're not as acidic as the proton on the end of an alkyne would be. This is more acidic than those. And that hybridization of the orbitals there are sp. And so you have a situation where you have 50% s orbital, 50% p orbital present. And the higher the S ratio in that hybrid orbital that proton lives in, the more acidic it's going to be. It can be closer to the nucleus with the higher S because S is spherical in shape. It doesn't have any nodes. And so the closer to the nucleus it can live, the more stabilized that negative charge will be when we form the conjugate base. So that makes that proton more acidic for an alkyne than it would for like an alkene or an alkane, because that conjugate base is more stable. So remember, the acidity of something depends upon the stability of the conjugate base. So when we form what's known as the acetylene anion, which is what that species is called when we remove that proton there, that is actually a rather stabilized anion and can function in a whole host of other reactions as a good nucleophile. And so that's why these reactions that we'll look at are kind of special to alkynes, because they first involve the formation of an acetylene anion. So now let's look at some of these organic bases and kind of how they're named and how you identify them. So these organic bases, these 3, are strong enough to deprotonate that terminal alkyne. The first one is called sodium amide, that's NaNH2. So that is made up of a positive sodium cation, and the amide ion is NH2 minus. It's a little confusing because we learned an amide functional group, and then we talk about sodium amide, which is not quite an amide functional group. That just happens to be the name of that anion. So they both just have the same name. So together you have a neutral species NaNH2. The next is called a Grignard reagent. A Grignard reagent is an organometallic reagent where we have usually some carbon chain, which is represented by the R group, and then magnesium with a halide, which is represented by the X group. So for example, I could write just any Grignard reagent, MEMGBr. How we would name this is methyl magnesium bromide. And in this Grignard reagent, the R group happens to be a methyl, and the halogen, the X, happens to be bromide. So the identity of both of those can change in a given Grignard reagent. When we're looking at a Grignard reagent, it's actually the carbon group that is going to function as a base grabbing that terminal proton. So this is where the electrons come from. This is where the grab of that terminal proton is initiated, not from the magnesium, not from the bromide. It comes from the carbon. And that's the same thing with the alkylithium. So RLI, that R group can change. And how we would name that is, for example, let's make up an alkylithium here, BULI. This would be called butyl lithium. And so this is a really strong base. It's a great base to use, except for it's a little bit dangerous. And when you show it grabbing that acidic proton. It's the butyl group, it's that carbon that grabs that proton. So you could see a variety of Grignard reagents. You could see a variety of alkylithiums by changing the R groups or the halogen, but you would just want to be able to recognize that that's what they are. And at this point, you just need to know that they're functioning as a base. We'll talk about Grignard reagents and alkylithiums more in depth next semester as well, and kind of talk about some of the finer details of them. But for now, we're just using them as a base to remove that acidic hydrogen on a terminal alkyne. So the first part of any of these mechanisms involving a terminal alkyne is we're going to deprotonate that acidic proton using any one of those three reagents. So you would just pick one of them. So here we have three examples. We have sodium amide, methyl lithium, or ethyl magnesium bromide. Those are all strong organic bases. So let's show how we would show that deprotonation using any of these. If you're using sodium amide, you would show it from the nitrogen. There's a lone pair of electrons on that nitrogen that can act as a nucleophile or a base and grab that proton. If you were showing it coming from the methyl lithium, you would start your arrow on the carbon, the methyl group in this case. And if you were showing it coming from the Grignard reagent, you would start your arrow on the ethyl group. So that's where those arrows would initiate on any of those bases. And then they would grab that proton, and the electrons in between carbon of the triple bond and the proton would go over and stay in that sp orbital on the end of the alkyne, forming our acetylide anion. So notice there's a negative charge right here now sitting in that sp hybrid orbital. So that now is going to act in a second step, depending upon what we're reacting it with, as a very powerful nucleophile. It's ready to react. And the side products that are formed, you don't have to show them, but they change depending upon if you're using sodium amide, a Grignard reagent, or ethyl magnesium bromide. For example, if you use sodium amide, you form ammonia gas as a side product when you grab that proton. If you were using methyl lithium, you would form propane or CH4 as a side product. Oh, I'm sorry, you'd form methane, I mean to say. In this case, we used methyl, not propyl. And using the Grignard reagent, in this case, we have ethane as a side product. But notice that all three of these are gases. And so by using something that forms a gas as a side product, they bubble out of the reaction and they leave the reaction flask. And you might recall that when we talked about Le Chatelier's principle, if you remove something, you shift the reaction towards that removal. So in this case, we would shift the reaction towards the right, towards the formation of our acetylide anion. So all of these are really good for driving the reaction forward, all of these gases that bubble out of the reaction, because it helps us actually create the acetylide anion that we need for the next step. Let's start with the synthesis of internal alkynes. So starting with our terminal alkyne, let's say that we want to make a different alkyne now. This is a pathway in order to make one. So we're going to start with using one of our bases. So let's use sodium amide in this case. The lone pair of electrons on the nitrogen will grab the proton. The electrons will swing over and stay with the carbon of the triple bond, forming the acetylide anion. That acetylide anion now acts as a nucleophile, and we're going to use an alkyl halide as the second step here. So the identity of this alkyl halide could change depending upon what product we're trying to form. In this case, we have a secondary alkyl halide with a bromo group on it. The identity of the halogen could change as well. It's just a good leaving group. So when our acetylide anion attacks, it's going to attack the electrophilic center. We know that bromide is more electronegative, therefore the carbon it's bonded to will be more electropositive. So our nucleophilic acetylide anion will attack that carbon, and it can't have more than 4 bonds. So once that attack happens, we end up booting off this bromo group. It has to leave. This is referred to as a good leaving group, or in other words, GLG. So that bromide that gets kicked off, we would leave Br minus. That is 8 valence electrons. It's a relatively electronegative atom. It can stabilize that charge. So that's why it's actually a good leaving group in the first place. So the end result, though, is that a new bond is formed from here to here. So it's just a single bond, but I'm just highlighting it. There is a bond formed between the triple bond and where we had the halogen on the other molecule. So this kind of looks a little funky. Let's redraw this. We have our triple bond, we have our new bond here, and then kind of show this with the correct orientation. 4 carbons over here. So notice 1, 2, 3, 4. And in our halogen, we had 1, 2, 3, 4. Where our bromo group was coming off of position number 2 right there. And that's where that new bond is formed in between our terminal alkyne and then the alkyl halide that we use in the synthesis reaction. So in the end, you end up creating an internal alkyne, and you can change what this alkyne is by changing your starting materials. We can also use acetylide anions to create different degrees of alcohols by changing the reagent that we react the acetylide anion with. So starting with our terminal alkyne, let's use our second reagent, the methyl magnesium bromide, as our base to deprotonate. We would show our arrow coming from our methyl group, the carbon. The electrons would stay with our carbon of our sp hybrid orbital, forming our acetylide anion. Now imagine in the second step that we react with formaldehyde. Formaldehyde is the simplest of aldehydes where there is a hydrogen on both sides of the aldehyde. So we have a carbonyl, and the carbon of the carbonyl is going to be our electrophilic center because our oxygen is going to be partially negative. And so our acetylide anion is going to want to attack that carbon. And when it does, one of the bonds of the double bond has to break and move up to the oxygen, so there's not more than 4 bonds on that carbon. So those electrons will swing up to the oxygen, forming an alkoxide anion. So we have a new bond that's formed here, just like we did last time. Our triple bond is still intact, and that new bond goes to the electrophilic center, that carbon that was attacked. We also have an oxygen with a negative charge now. That's our alkoxide anion. So in the following step, we have to use an acid source in order to protonate our oxygen and get rid of that negative formal charge. So often H3O plus will just be written to indicate that we're using some acid. That identity of that acid could change. So our oxygen will act as a nucleophile or a base and grab that proton from the acid. And those electrons will swing over and stay with the oxygen, forming water as a side product. So minus H2O. And that would give us a primary alcohol in this case for our product. Primary because those 2 hydrogens were part of the formaldehyde. So when we look at the alpha carbon, how many carbons are coming off of the alpha carbon? Well, just 1 right here from that triple bond that was the terminal alkyne that was added to our formaldehyde. So this would be primary in this case. Now the next 2 mechanisms for secondary alcohols and tertiary alcohols are basically going to be the same series of steps that we just saw for primary alcohols. What's going to change is what is being reacted with the acetylide anion. So when we're forming a secondary alcohol, we're not using formaldehyde specifically, but we're using some aldehyde, and the aldehyde can change, meaning the R group off of the aldehyde right here can vary. So starting off, we have our alkyne, we have our terminal alkyne, and we're going to need to deprotonate that. So let's say that we used butyl lithium. We would show coming from the butyl group, grabbing that acidic proton. The electrons will move over and form the acetylide anion. The acetylide anion will act as a nucleophile and attack the electrophilic center of our aldehyde, whatever that aldehyde is. The electrons of the double bond will swing up to the oxygen, forming the alkoxide anion. We have our new bond between our alkyne and our electrophilic center. Our oxygen has a negative formal charge. And in that final step, we have to protonate that alkoxide anion, that base. And so we add some acid. The alkoxide anion will then grab a proton from the acid. The electrons between the oxygen and hydrogen will stay. That gives us our water side product. And notice now we form a secondary alcohol. So it's the same set of steps that we used for the primary alcohol, only when you look at the alpha carbon, now there's a carbon here and a carbon here, and only one proton coming off. So the number of carbons surrounding the alpha position is how you define an alcohol, whether it's primary, secondary, or tertiary. So the identity of the aldehyde can change, which means that this R group here coming off can change as well in the final product. The identity of the terminal alkyne can change as well. But you still need to use some aldehyde and an acid in order to make a secondary alcohol versus the formaldehyde specifically for the primary alcohol. And last but not least, you can maybe imagine how this would change just a little bit in order to create a tertiary alcohol. After you form the acetylide anion, you would use some ketone. And so with the ketone, you can have an R group here, and you can have a different or the same R group on the other side. So the identity of that ketone can change as well. So if we are using an alkylithium, maybe, or a Grignard reagent, we would start with that carbon, the methyl group on the methyl magnesium bromide, can grab that acidic proton. The electrons can swing over, forming our acetylide anion, which is now our nucleophile, the next step. The negative charge on the carbon will attack the electrophilic center of the ketone. The electrons swing up, give us our alkoxide anion. The alkoxide anion grabs a proton from an acid source in a final step. Electrons swing over and we form oxygen, a water side product. And we end up with our tertiary alcohol final product. So on our alpha carbon, we have a carbon here, and a carbon here. So that's why it's a tertiary alcohol in this case. So all three of these last mechanisms, I only went through them step by step just for a little bit of practice for you guys, but you can see that they're the exact same series of steps over and over again. We're just changing the reagents in each case, and the reagents all contain a carbonyl, so they function similarly because they have that carbonyl functional group, whether it's an aldehyde or a ketone. And actually in the second half of this class, when we study aldehydes and ketones, we do them together. We look at all of their reactions together because they undergo pretty much the same reactions due to them just containing a carbonyl for their functional group. So this is how you can create primary, secondary, or tertiary alcohols when using a terminal alkyne.